So today we're going to talk about the IEEE 32 standard bit floating point notation. As you can see on the board here, it is broken into three segments. We have the sign bit represented only as 1 bit, the exponent, which is represented in 8 bits, and the end, which is called the mantissa, represented in 23 bits. Now, we're going to do a practice problem just to walk you through the steps on how to solve a decimal to floating point conversion. So, problem 1. We're going to have a decimal number of, say, 13.125, and our first step is to convert our decimal number into binary. Now here, represented in 4 bits, is 13. Here being the number 8 plus 4 and 1. If you add all these together, equals 13. Same here. This is 1/2. This is a quarter. This is 1/8. An eighth in decimal is 0.125. Now, we take this and we put it into scientific notation. Now, we can do this by moving over the decimal point 1, 2, 3 spaces, represented right here. Now, we break it into the IEEE 32-bit standard notation. So we have our sign bit here, and that determines whether it's a positive or a negative number, which it is indeed positive, so we'll represent it as 0. Then 8 bits for our exponent value, and then the rest of the bits is our mantissa. So, first step after the sign is we write down the mantissa into its appropriate location. So we write it down. And that's everything after the decimal point. 1 0 1 0 0 1. Now we take care of the exponent. The way we do this is, so we add our exponent to the standard 127, and that will give us the approximate or the appropriate value that we can store in binary into the exponent value. Our final step is to convert it into hex. Alright, so here is our floating point notation. Now, our final step is to convert all this binary into hex. So now we can do this by cutting into 4s, because each hex digit is represented by 4 binary bits. So this is 4. The next 4 here is represented by 0001, which is 1. Following 4 represented by 0101, 5. And then the remaining 1001, 9. And since this is 32-bit standard, we're going to have to fill in the rest with zeros to give it 32 bits. Now you have your hex value, which you can then interpret. So now for problem 2, I'm going to show you how to convert from hex into regular decimal using floating point notation. So here I already laid out the general format for you. Again, we have our sign bit, our exponent field, and our mantissa. Now, we are given the hex number BF400000. Now, our first step is to break each individual hex digit into binary. So, for B, we're going to write 1011 for B. So on for F, 1111. And for 4, 0, 1, 0, 0. And now the rest are zeros, and it goes on for 32 bits. So we'll just say ... for right now. Now, as you can see, our sign bit is 1, which means that it's going to be negative. And here, now as you can see, our exponent field is normalized, and we're going to have to denormalize it to get the real exponent. So here we represented our hex number into binary. So we already have our sign bit, and now is our exponent field, and we need to get the actual exponent by using our bias exponent. So we'll do that now. This right here, 126. We'll subtract our bias from it. And our bias is always going to be 127. So now that is going to equal -1, which is our actual exponent. So now we're going to use this and formulate our binary expression. So we always write down 1 because we need a placeholder in our decimal point. Then we're going to plug in our mantissa, which in this case is 1 followed by all zeros. Now, it is a negative number, so that's what we're going to do now. And since the exponent field is -1, and we found that by taking our exponent field and subtracting it by our bias exponent. And we're going to put this into scientific notation. Our base number is 2 because we're in base 2 binary. And we're going to plug in our -1 field. So this is our represented value from our floating point notation. Now we're going to simplify this even further by taking away the scientific notation. And we'll do this by moving the decimal point 1 placeholder over. So -1, we move it forward. If it was positive, we'd move it back. So our new represented value is going to be -0.11, followed by all zeros because it is 32 bits. Now, we have to. This is not our final step. We're going to have to convert this into decimal. So we can do this by simple conversions. Now, our first step is, or our first placeholder is going to be 1/2. Then is going to be 1/4, and then 1/8, so on and so on. So 1/2 in decimal is 0.5. So we're going to add that here, 0.5. Our next one is 1/4, which means 0.25. So we're going to add 0.5 to 0.25, and we're going to get 0.75. So now we're almost done. Throw in our negative, 0.75. And this is going to be our decimal value for our original hex numeric value. And that is how you convert from hex into decimal using the IEEE 32-bit standard floating point notation. Now, our first step is to put down our sign bit. Now, this is our first step. Okay, hold on. Now, in order to do this, we're going to use this formula. Hold on. Pause it. There's something wrong with my notes.
Okay. Go for it.
Alright, so as you can see here, we have our sign bit, our exponent bit, and our mantissa. Now, we're going to have to use our bias exponent to convert the exponent field to get our actual exponent. So we'll do that now. Now, our bias exponent is 127. Now we're going to have to subtract this in order to get our exponent. And this is negative 126. Doesn't get us here. Look what I have in my notes. 127 minus 126 equals E. E equals negative 2. That's not right at all.
Why would it equal E?
So our bias is there, and since this is a negative number, we have to... Doesn't make any sense. Oh, it's that minus the bias. I have to do this again. Sorry.
Just start from where you did last time.
Yeah, okay. All right. What did I say last time?
Here we have our represented.
Oh, okay. Of how to solve. So how to solve